History of Math, Lecture 21, and I was asked to do the first two problems of homework 8. So this is just to do some numerical examples of a general fact, which you're asked to prove in part of the program. So we have the binomial coefficient 5 choose k, and we want to compute this for k equal 1, 2, 3, and 4. So in general, if you have the binomial coefficient n choose k, you can write it in several ways. One is n factorial over k factorial times n minus k factorial. So, and you remember that n factorial is just the product of the positive integers from 1 up to n. Or you can divide part of n factorial by n minus k factorial. So in the numerator, you have just k numbers starting with n and decreasing by 1. So the last number will be n minus k plus 1. Divided by k factorial. So 5 choose 1 is 5 over 1 is 5. 5 choose 2 is 5 times 4 over 2 times 1. That's 20 over 2, or 10. 5 choose 3. Again, we have 3 numbers in the numerator, starting with 5 and going down. So 5 times 4 times 3 over 3 factorial. So 5 times 4 is 20 times 3. This is 60 over 6, which is 10. 5 choose 4. 5, 4, 3, 2 over 4 factorial. Actually, you can see the 4, 3, 2 cancels the 4, 3, 2 in the denominator, and that's just 5. And you see these are all divisible by 5. Any question about that?
No.
Okay, so that's part A. Part B is to do the same thing where 7 is the numerator in the binomial coefficient. So we're looking at 7 choose k. So let's do some calculations. 7 choose 1 is 7 over 1 is 7. 7 choose 2 is 7 times 6 over 2. That's 42 over 2 is 21. 7 choose 3 is 7 times 6 times 5 over 3 times 2 times 1. 3 times 2 is 6. That cancels the 6 in the numerator. This is 35. 7 choose 4 is 7 times 6 times 5 times 4 over 3 times over 4 times 3 times 2 times 1. We can just look at cancellation because the 4 cancels the 4, the 6 cancels the 6. And again, we have 7 times 5 or 35. 7 choose 5. Well, I'll do it the long way. That's 7, 6, 5, 4, 3 over 5, 4, 3, 2, 1. Again, the 5s cancel, the 4s cancel. The 6 cancels the 6. 7 times 3 is 21. And then finally, 7 times 6, 7, 6, 5, 4, 3, 2, 6, 5, 4, 3, 2, 1. Here we have the product of this is 1 through 6, which is the same as 2 through 6. They cancel, this is 7. So if you look at the numbers, when you have these binomial coefficients, 7, 21, 35, 35, 21, 7, they're all divisible by 7. Okay. Is that all right? That's just a calculation. And this is these are 2 special cases of the general fact, which is part 1C, that is, if P is prime, and k is any number from 1 to p minus 1, we have to prove p choose k is divisible by p. So if you look at p choose k, that's p minus 1, p minus 2, down to p minus k plus 1. This is k integers, starting with p and going down by 1, over k minus 1, k minus 2, going down to 1. But k is between 1 and p minus 1. So if you look at this denominator, no number less than k, no number k strictly less than p is divisible by p. So there is no p here, right? These are all numbers strictly less than p. P doesn't divide any of these numbers. So there's nothing in the denominator that can cancel the p in the numerator. So the p in the numerator is not canceled out by a p in the denominator. So when you take this number and you reduce it to lowest terms, it's always going to be an integer, in fact, but in any case, there's always going to be a p in the numerator, and that's what you had to prove. And the reason is that no number strictly smaller than p, no positive integer, strictly smaller than p is divisible by p. There's no p that comes up there. So that's the proof. That's a proof. Right. So this is something you have to think about, but yeah, you have to think about to make sure that you understand the argument and you understand why it's correct. Any questions about that? Problem 2 is just a series of calculations. If we take a squared minus 1, if a is equal to 1, that's 1 squared minus 1, which is 0, which is 3 times 0. It's divisible by 3. And if you take a equal to 2, 2 squared minus 1 is 3, which is divisible by 3, 3 times 1. So that's part A. Right? Just plug in a equal 1, you get 0. Plug in a equal 2, you get 3. In part B, so this is, so this says that 3 divides a squared minus 1 for all a between 1 and 2. If you try to do the same thing, let me just jump to part C. So if you look at part C, we look at, the idea is to show that 5 divides a to the 4th minus 1 for a between 1 and 4. So you need to check this. You have to check a equal 1, a equal 2, a equal 3, and a equal 4. So 1 to the 4th minus 1 is 1 minus 1 is 0, is divisible by 5. 2 to the 4th minus 1 is 16 minus 1 is 15, is 5 times 3. 3 to the 4th minus 1, 3 to the 4th is 81. 81 minus 1 is 80, which is 5 times 16. 4 to the 4th minus 1, let's see, what is 4 to the 4th? 4, 16, 64, 256 minus 1 is 255, which is 5 times 51. So all of these numbers are divisible by 5. Let's look at part E. So we want to show that 7 divides a to the 6 minus 1 for a between 1 and 6. So you just do that calculation. 1 to the 6 minus 1 is 1 minus 1 is 0, is 6 times 0. 2 to the 6 minus 1. What is 2 to the 6? 2 to the 6 is 64. 64, sorry, and this is 7 times 0. I'll show it's divisible by 7. 64 minus 1 is 63, which is 7 times 9. What is 3 to the 6th equal? It goes 3, 9, 27, 81, 243, 729. 729 minus 1 is 728, is 7 times 104. Right? And you just do the calculations for, let's see, I just did 1, 2, 3, 4, 5, and 6. I'll do one more. What is 4 to the 6 minus 1? Let's see, 4 to the 6 is the same as 2 to the 12th. 2 to the 10th is 1024, 2048. That's 4096 minus 1. That's 4095. I'll take a scrap of paper and divide 7 into 4095. That's so when I do my, this is 7 times 585, and so on. So for these three cases, where I'm looking at the prime 3, 5, and 7, the prime divides a to the p minus 1 minus 1. So these are parts A, C, and E. And if you look at parts B and D, you see that this doesn't have to happen if your modulus is not a prime. So in part B, we're looking at a cubed minus 1 for a equal 1, 2, and 3. Right? So 1 cubed minus 1 is 0. Well, that is divisible by 4. 2 cubed minus 1, 8 minus 1 is 7, is not divisible by 4. 3 cubed minus 1 is 27 minus 1 is 26, is also not divisible by 4. All right, so 4 doesn't divide a cubed minus 1 for all these a's. In part D, we're looking at divisibility by 6, and we're looking at a to the 5 minus 1 for a equal 1, 2, 3, 4, and 5. So 1 to the 5th minus 1, 1 minus 1 is 0, is certainly divisible by 6. But 2 to the 5th minus 1, 32 minus 1 is 31. That's not divisible by 6. And you can try others. I mean, maybe they are, maybe they're not. 3 to the 5th minus 1. What is 3 to the 5th? So the powers of 3 are 3, 9, 27, 81, 243. 243 minus 1 is 242, not divisible by 6, and so on. You can check 4 to the 5th and 5 to the 5th. In fact, you don't have to, because the statement, the problem is, prove that 6 does not divide a to the 5th minus 1 for all of these a's. Well, as soon as you find one counterexample, there it is, you're done. So you can stop at that point. Okay. So problems 1 or 2, problem 2 is only calculation. And in problem 1, parts A and B are calculation, and part C was a proof. So I hope you had a chance to look at the review sheet for the exam on Wednesday. I'll go through the problems, as many as I have time to do. Right, but are there any questions before I start that?
Yeah, Professor, from homework number 8, where it says, from homework 8, number 3, to sketch the proof. I was just looking through the book, but I don't see any, like I see the examples, but not the sketches.
Well, let's see. This is Euler's number theory, and let's see where it is. So this is the theorem on page 228. And it uses the two theorems on the two previous pages. On page 226 at the bottom of the page, there's a theorem, which was basically the homework problem I just did, though the proof in the book is different. And yeah. So it's, yes. So the theorem on page 228 is exactly problem 3, and the proof is basically already done on the previous page on the proof on page 227. Yeah, I mean, that's where it is.
Okay.
Okay, so let me find the review sheet. That'll make things easier. Okay. So the first couple of questions I don't really need to go over. The exam covers the material in chapters 6 to 10, which is in homeworks 5, 6, 7, and 8. So you should review those problems. As I've said always, you're expected to know in each chapter what is labeled the great theorem. We've talked about various great mathematicians from the 18th century, beginning of the 19th century: Newton, Fermat, Leibniz, Euler, Gauss. So you should know something that each of them has done, and there are chapters devoted to them. So you just have to know something. And then there are a series of additional problems. So let me just start them with number 4. So this is from the review for exam 2. We have a cubic, so this is number 4. We have a cubic equation, x cubed plus 9x squared plus 2x minus 6 equals 0. And you want to make a substitution to get from this the depressed cubic. So if you let, let's see, y equal x minus 3, let's see what happens. If you if you let x equal y minus 3, if you make that substitution, what do you get? So x cubed is y minus 3 cubed, plus 9, x squared is y minus 3 squared, plus 2x is 2 times y minus 3 minus 6. If you expand this, y minus 3 cubed is y cubed minus 3 times 3y squared plus 3 times 3 squared y minus 3 cubed. As if you expand this, this is what you get. Y cubed minus 9y squared plus 27y minus 27. Then we have here plus 9 times y minus 3 cubed. Y minus 3 cubed is y squared minus 6y plus 9, plus 2 times y minus 3 minus 6. So here I have this, which is x cubed minus 9y squared plus 27y minus 27. I have plus 9y squared minus 54y plus 81 minus 2y minus 6 minus 6 equals 0. The important point is that the 9y squared and cancels the 9 minus 9y squared. So I'm left with y cubed. I have 27y minus 54y. That's minus 27y minus 2 minus 29y minus 27 minus 6 minus 6 minus 12. So that's minus 39. 81 minus 39 is 42. So, unless I made some arithmetical mistake, which is possible, this is the depressed cubic that comes from this cubic. Okay.
So let's just say on the exam, you made a mathematical error and you got the depressed cubic. How much points would you get wrong since we can't use calculators?
Well, first of all, calculator wouldn't help you with this.
But let's just say like one of the simple you got the signs mistake, or when you did
so
that.
you'll lose a couple of points. I mean, you'll get, most of the credit. If you set it up properly, but the mistake is just in the arithmetic, you'll lose a couple of points, not very much. Yeah. That's the way I graded the first exams, the way I always grade exams. It's not all or nothing. It's not that if you get it wrong because of some mistake, you get a 0, but there's partial credit always. Part B, we have another cubic, 3x cubed minus 11x squared plus 10x equals 0. So we have to make a substitution.
Can you move the paper down, please?
Sorry.
Thank you.
So what is the substitution that we should make in here? X is equal to what? Someone tell me what the substitution is?
Let me get my pen.
Let's make believe we don't know what the substitution is. We just know we're going to let x equal to y plus c for some c. And then we want to figure out what that c would have to be. So we would have 3, replace x by y plus c. y plus c cubed minus 11 y plus c squared plus 10 y plus c equals 0. So if you expand this, this is 3 times y cubed plus 3cy squared plus 3c squared y plus c cubed minus 11 y squared plus 2cy plus c squared plus 10y plus c. And the important point is you want to get rid of the y squared term. Here you have 9cy squared. Here you have minus 11y squared. So for them to cancel, you want 9c to equal 11. So c is going to equal 11 over 9. If you let c equal 11 over 9, you will get cancellation. So then you're left with what? 3y cubed plus 3c squared, 11 over 9 squared, plus c cubed, 11 over 9 cubed, minus, this is canceled, 22, 11 times 2, 22c, 11 over 9y, and then you have your constant terms, 3c cubed minus 11c squared plus 10 times 11 over c. Maybe I forgot the 10y in here, plus 10y. And you work it out. I don't need to work it out now because on the exam, you won't have a problem that requires so much arithmetic. But this is the depressed cubic. The important thing is to know what the substitution is. In general, if you have ax cubed plus bx squared plus cx plus d equals 0, the substitution is going to be x equals b over 3a minus b over 3a. That's the substitution. So in this case, b was minus 11, a was 3, so x equal minus b over 3a is minus 11 over 9, which is what we got.
So when you do the previous problem, you already put in the numbers into the formula to get the substitution. That's what
Well,
you
so, sorry. So if you have ax cubed plus bx plus cx, if you have your cubic, you can either remember that the correct substitution is x equal to y minus b over 3a, or if you don't remember it, you can just say, okay, suppose I substitute x equal y plus c, what does c have to be? And then you can do the arithmetic and you find out that's what it has to be. There's only one substitution that will eliminate the quadratic term.
Professor, how did the 3a become 9? You multiply 3.
I'm sorry, your sound is kind of garbled. Could you repeat what you said, please?
I said, why is 3a became 9? How did 3a become 9?
How did 3a become 9?
Yes.
Well, a is equal to 3. So 3 times 3 is 9. In this,
Where did
cubic-
you get the 3?
from
the. Okay.
right, it's ax, the standard notation, ax cubed plus bx squared plus cx plus d. So in this example, a is 3 and b is minus 11. In this particular example. So the general substitution is minus b over 3a. So if a is 3, the denominator is 3 times 3, or 9.
Okay. Professor, for the previous problem we did, how did you came up with substituting y minus 3?
In this problem,
Yes.
so A is equal to 1, B is equal to 9, X is Y, you make the substitution minus, what did we just see? B over 3A. So that's Y minus B, which is 9 over 3 times 1. 9 over 3 is 3. Right? That's the general substitution.
So it's always b over 3a?
Yes,
Okay.
yeah,
See, that's-
minus B over 3A.
That's where I see like a lot of the confusion comes from, because every time we did a problem with the cubic, you would find what the substitution would be and you would plug it in immediately. So every time we did one, it would be a different number, but
Well,
like we skipped.
the numbers depend on the particular cubic, but there's
Yeah, but
only
we
one
always-
formula for the substitution.
Yeah, and that's the problem, because like we never, sometimes the formula is not there. So when we see a new equation to substitute in, we don't know where you got
Right.
that. But I see now.
Well, I mean, I'm sure this is in the text, and I'm sure at some point, maybe at the very beginning,
Yeah, we discussed that. Yeah.
we discussed that, yeah.
So going back to the second problem,
Yeah.
it doesn't have to be monic, correct? It doesn't. That's irrelevant.
Well, so it's easier if it's monic, because then you're just dividing A is equal to 1. But if it's not monic, as in this case, the leading coefficient was 3, then, again, the substitution is minus x equal y minus b over 3a. So a is the leading coefficient. If it's 1, it's 1. If it's not 1, it's not 1. But whatever it is, it's just arithmetic.
Copy.
Okay. And then the next problem was to actually use Cardano's formula to solve some cubics. So the first cubic was already given in depressed form, x cubed plus 2x equals 135. So Cardano's formula says the following: if your cubic is in the general form x cubed plus mx equal n, so in this case, m is 2 and n is 135, you calculate these two numbers, t and u. So t is the cube root of n over 2 plus the square root of n squared over 4 plus m cubed over 27. U is almost the same thing, except with a minus sign, minus n over 2 plus square root of n squared over 4 plus m cubed over 27. And the solution x is t minus u. So in this case, t is the cube root of n over 2 plus the square root of n squared over 4 plus m cubed, 8 over 27. U is the cube root of minus 135 over 2 plus the square root of 135 squared over 4 plus 8 over 27, and x is t minus u. And you can stop at that point, obviously, because there's no way to compute that by hand or even figure out what it is. It's just a matter of plugging the numbers into Cardano's formula.
Professor, this is the formula for Cardano.
Well, are you asking me that as a question? Because the Cardano's formula is just written down in the book. So you open the book and you look up the formula. That is the formula. But it's in the book. I mean, that's right. I mean, you're supposed to know what's in the book, and you know, a lot of work is spent developing to prove this, but this is the result. If you look in the text, it is on page 145. Okay. The next problem has to do with expanding various functions into power series, using Newton's binomial theorem. And Newton's binomial theorem is a generalization of actually kind of a typo here. I think what I put in the sheet was to expand. This is problem 6a. To expand 1 plus 5 to the 5th, which is kind of silly, but I mean, it's really just 6 to the 5th, whatever that is. So, I mean, let me just calculate. What is 6 to the 5th? 6, 36, 216. So, but if you were going to expand this 1 plus 5 to the 5th, this would be 1 plus 5 times 1 plus 5 times 4 over 2 times 5 squared plus 5 times 4 times 3 over 3 factorial 5 cubed plus 5 times 4 times 3 times 2 over 4 factorial 5 to the 4th plus 5 times 4 times 3 times 2 times 1 over 5 factorial 5 to the 5th. If you do the arithmetic, this is what you'll get. But I really, I'm sure, meant to write 1 plus x to the 5th. And so let me expand that. This is just the usual binomial theorem. It's 1 plus 5 times x plus 5 times 4 over 2 factorial x squared plus 5, 4, 3, 2 over 3 factorial x cubed plus 5, 4, 3 over 3 factorial, 5, 4, 3, 2 over 4 factorial x to the fourth plus 5 times 4 times 3 times 2 times 1 over 5 factorial x to the fifth. And if you try to do another term, when you start with 5, and if you go down 6 numbers, you would get to 0. So you would just get 0 from that every point on. So this is 1 plus 5x. 20 over 2 is 10x squared. Plus 10x cubed plus 5x to the fourth plus x to the fifth. This is just expanding 1 plus x to the fifth by the binomial theorem. And it just turns out there's 6 terms there. If you're going to expand 1 over 1 plus x, which is 1 plus x to the minus 1, so this is 1 plus minus 1 over 1 times x plus minus 1 minus 2 over 2 factorial x squared. Right? Remember, the rule is always the following. If you have 1 plus x to the power, I don't know, well, let's say 1 plus x to the power n, but n doesn't have to be an integer. This is 1 plus n times x plus n minus 1 over 2 x squared. In general, you will have n minus 1, n minus 2. You have a product of k integers. Sorry, not necessarily integers, n numbers. Sorry, for the kth term, you'll have k numbers starting with n and decreasing by 1. And this goes on forever, except it might be if n is a positive integer, at some point these are all 0. So in this case, n is minus 1. So you get 1 plus minus 1 over 1x, minus 1 minus 2 over 2x squared, minus 1 minus 2 minus 3 over 3 factorial x cubed. Let me just put that in a box because the next 2 terms will be minus 1 minus 2 minus 3 minus 4 over 4 factorial x to the fourth. And the next term will be minus 1 minus 2 minus 3 minus 4 minus 5 over 5 factorial x to the fifth. So that's 6 terms. What do we have here? 1 minus 1 over 1 is minus x. Minus 1 minus 2, when you multiply them, you get 2 over 2 plus x squared. Here I have minus 3 factorial over 3 factorial minus x to the cube. Here I have 4 minus sign, so that makes it plus 4 factorial over 4 factorial x to the fourth minus x to the fifth. So 1 over 1 plus x, when you expand it by the binomial theorem, it starts like this. It's the alternating sum of powers of x. In part C, again, the binomial theorem. One over 1 minus x cubed, which is 1 minus x cubed to the power minus 1. That's the power. So this is 1 minus or if you like 1 plus minus 1 over 1, and this is, I can write this as 1 plus minus x cubed to the minus 1. So this is minus x cubed. And then the next term is minus 1 minus 2 over 2 factorial minus x cubed squared. And the next term is minus 1 minus 2 minus 3 over 3 factorial minus x cubed cubed. And the next term is minus 1 minus 2 minus 3 minus 4 over 4 factorial minus x cubed to the 4th. And the next term is minus 1 minus 2 minus 3 minus 4 minus 5 over 5 factorial minus x cubed to the 5th. So here this is minus 1 times minus x cubed, that's plus x cubed. Here I have 2 over 2 minus x cubed squared is plus x to the 9th. Here I have minus 3 factorial over 3 factorial. But here I have minus x cubed cubed, so this is going to be a minus sign. Minus times minus is plus x to the 27th. Here I have 4 factorial over 4 factorial. I'm raising this to the 4th power, which makes it positive. So I have x cubed to the 4th, x to the 81. Again, I'm just going to get all positive signs, and I'm going to get the sum of the powers of x to the powers of 3. The powers of 3, 3, 9, 27, 81, 243, and so on.
When you do the powers of the exponent, you just multiply them, right?
I'm not sure what you mean. Which is the exponent?
So when you have like a negative x cubed to the raised to the 2nd, you just put 3 times 2, right?
No, it's 3 squared. That's why I don't have a 6 here, I have a 9. It's not 3 times 2. It's 3 to the power 2. Right? This is 3 squared. This is 3 cubed. These are, right? I mean, in general, I mean, if you have x, or maybe this is what you mean. If you have x to the AB, that is x to the a times b. So
Yeah,
x to the 3 squared is, sorry, maybe I did this wrong. Let me just double check. X cubed cubed, x cubed, this is x to the 9th. Oh, I'm sorry. I think I made a mistake and you corrected me. So x cubed times x cubed is x to the 6th. X cubed times x cubed times x cubed is x to the 9th. X cubed times x cubed times, this is x to the 12th. Yes. I mean, this is the formula for powers. X to the a to the power b is x to the ab. So x to the 3 squared is x to the 3 times 2, or x to the 6th. So this is x to the 15. Yes. You get, yeah. Right. You're getting the powers of x cubed, but the powers of x cubed are x cubed, x to the 6th, x to the 9th, and so forth. It's not those raised to the exponents. Thank you. And so this is not correct. Yeah.
So you know how you have to have it in the formula 1 plus x to whatever number. If you had a number instead of 1, you have to factor out that number in the beginning.
Yes. Right. At least using this this simple form of the binomial theorem. If you had yeah, I mean, if you had a plus x to the power n, you could write that as a to the n times 1 plus x over a to the n, and then
You would-
expand this by the binomial theorem.
So-
So you will get x a to the n times 1 plus n, x to the a, and so forth.
Okay.
Okay, let's see. Oh, and then the last one again. If you have 1 plus x cubed square root, that's 1 plus x cubed to the power of half. So when you expand this, you would get 1 plus a half over 1 x cubed plus a half times a half minus 1 over 2 factorial x cubed squared plus a half minus 1, a half minus 2 over 3 factorial x cubed cubed, and so forth. So this is 1 plus a half x cubed. What is this? This is a half times minus a half is minus a fourth over 2 is minus an eighth x to the sixth. This is a half times minus a half minus a fourth. A half minus 2 is minus 3 halves. Let me just do this bit of arithmetic. A half times a half minus 1 times a half minus 2 is a half times minus a half times minus 3 halves. The minuses cancel. You get 3 over 8. So this is 3 over 8 over 3 factorial. That's 3 over 8 over 6 is 3 over 6 times 8. 3 into 6 is 2, so it looks like it's 1 over 16. So this is plus 1 over 16 x to the ninth, and so forth. That's what these coefficients end up looking like. Problem 7 starts with recalling the geometric series. It says that if x is a number between minus 1 and plus 1, if you take summation x to the n goes from 1 to infinity, which is x plus x squared plus x cubed, and so forth. Actually, the form we usually see for the geometric series is when you start with n equals 0. So that you have a first term 1 plus x, and so forth. This equals 1 over 1 minus x. And so summation n goes from 1 to infinity, x to the n. It's just like summation n goes from 0 to infinity, x to the n, except we put in the number 1, so you have to subtract 1. So this is 1 over 1 minus x minus 1. So you have to know fractions, I guess. This is 1 over 1 minus x minus 1 minus x over 1 minus x, which is x over 1 minus x. So if you take x to be equal to a seventh, summation n goes from 1 to infinity, 1/7 to the n, is equal to, when x is a seventh, 1/7 over 1 minus a seventh, which is 1/7 over 6/7, which is 1 over 6. But the formula for a geometric series, which you are supposed to have seen in Math 176, is something that everybody has to know. So that's the geometric series. The next problem, part B, involves what is called a telescoping series. We're looking at summation. N goes from 1 to infinity, and each term is 1 over 7 to the n minus 1 over 7 to the n plus 1. So it's always good, if you don't know the answer instantly, to write down the first few terms. When n is 1, you get 1/7 minus 1 over 7 squared. When n is 2, you get 1 over 7 squared minus 1 over 7 cubed. When n is 3, you get 1 over 7 cubed minus 1 over 7 to the 4th. When n is 4, you get 1 over 7 to the 4th minus 1 over 7 to the 5th, and so on. And you notice the minus 1 over 7 squared, 1 over 7 squared, you have minus 1 plus the other, they cancel. Minus 1 over 7 cubed plus 1 over 7 cubed, they cancel. Minus 1 over 7 to the 4th plus 1 over 7 to the 4th, they can't. Everything's going to cancel except the first term. That's the only thing that's left. So the sum is just the first term, 1 over 7. Any questions about this? Again, these are all techniques that are in Math 176, Calc 2, but what we're seeing here is where they come up in the history of mathematics. And these are core parts of 17th and 18th century calculus.
Could you separate the two into two summations and do it for each individual one?
Well, okay, so that's an interesting idea. You're saying, suppose you write this as summation, n goes from 1 to infinity, 1 over 7 to the n, minus summation, n goes from 1 to infinity, 1 over 7 to the n plus 1, right? Is that what you mean?
Yeah.
Okay, so let's ignore for the moment whether this is legitimate, but if you could do this, let's see. This is summation 1 over 7 to the n goes from 1 to infinity, minus summation. Now, if you look at n plus 1, as n goes from 1 to infinity, n plus 2 goes from 2 to infinity. So this is really like the sum from 2 to infinity of 1 over 7 to the n, right? Because when n is 1, this is 2. When n is 2, this is like the same series, but starting with 2. This, if you take away the first term, 1 over 7, and then you have everything else from 2 to infinity, 1 over 7 to the n, minus 1 over 7 to the n goes from 2 to infinity. And then you see these cancel, and you're left with 1 over 7. So something like that would be okay. Another way is, again, assuming this is legit, summation 1 over 7 to the n goes from 1 to infinity. If I factor out a 1/7, this is 1/7, summation n goes from 0 to infinity, 1 over 7 to the n. And this is a geometric progression. This is 1 over 1 minus a 7th, which is 1 over 6 over 7. The 7ths cancel. That's a 6th. And if I take this series, summation n goes from 2 to infinity, 1 over 7 to the n. If I factor out a 1 over 7 squared, this is 1 over 7 to the n. N goes from 0 to infinity. That's 1 over 49, and this is the geometric series, 1 over 1 minus a 7th. So I get 1 over 49 times 1 over 6 over 7. 7 into 49 is 7. This is 1 over 42. So this would give me 1/6 minus 1 over 42. And if I put that over, if I do the fractions, that's also equal to a seventh. So, what you said is if you did separate it into two series, that's not always legitimate. In this case, it happens that it is, but you would still get the same answer because there's only one answer. Let's see. Problem number 8 was to show that if you take summation 1 over n, where n starts from some power of 2 plus 1 up to the next higher power of 2, this is bigger than a half for all k greater than or equal to 2. So again, if you want to prove something like this in general, and if it looks complicated, you can start with like the simplest cases. So what is this when k equals 2? K is 2, k minus 1 is 1. So we're looking at the sum from n going to 2 to the first power, which is 2 plus 1, 3, up to 2 squared, 1 over n, which is a third plus a fourth. We want to show that's bigger than a half. So you can always just add them. If you add them, you get 7 over 12, which is bigger than 6 over 12, which is a half. Or you could just say a third is bigger than a fourth. So if I replace a third by a fourth, I get something smaller. And a fourth plus a fourth is 2 over 4, which is a half. Right? That's the case k equal 2. If I take k equal 3, so k minus 1 is 2, and 2 to the k minus 1 plus 1, 2 squared plus 1, that's 5. So I'm looking at the sum from n goes to 5 to 2 cubed, which is 8, 1 over n. This is a fifth plus a sixth plus a seventh plus an eighth. And again, I could add this up, but I just have to show it's bigger than a half. Each of these fractions is bigger than an eighth because the denominator 8 is smaller. So this is bigger than an eighth plus an eighth plus an eighth plus an eighth, which is 4/8, which is a half. And then you might get the idea that if you're summing from n equal 2 to the k minus 1 plus 1 up to 2 to the k, 1 over n, if you look at the numbers, this is 2 to the k, this is 2 to the k minus 1. The next one is 2 to the k minus 1 plus 1. So I'm summing up all the numbers in this interval. And how many numbers are there? 2 to the k minus 2 to the k minus 1 of them, right? I'm looking at all the numbers up to 2 to the k, but not taking any of the numbers up to 2 to the k minus 1. So I have this many numbers, which is exactly 2 to the k minus 1. And these numbers, the denominators are getting smaller. So the smallest number is the number with the largest denominator. So you have 2 to the k minus 1 numbers, and all of them are strictly bigger than 1 over 2 to the k, except for the 2 to the kth, but you have more than, so you have this inequality, and this is 2 to the k minus 1 over 2 to the k, which is a half. And that's what we wanted to prove. That's the proof. So this is one step and an alternate proof in chapter 8 that the harmonic series diverges. Any questions about this? I mean, there's serious mathematics here. It's all not super advanced. It's all actually, it's not advanced mathematics. But it's core mathematics, but requires some understanding. Problem number 9 was asking you to review the proof that the sum of the triangular numbers converges. So what are the triangular numbers? 1 plus 2, which is 3, 1 plus 2 plus 3, which is 4, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4, which is 10, and so forth. In general, the nth triangular number is the sum of the first n positive integers. And they teach you somewhere that if you look at the largest and the smallest number, they add up to n plus 1, 1 plus n. If you look at the next second smallest and second largest, 2 plus n minus 1, it adds up to n plus 1. You look at 3 and n minus 2, it adds up to n plus 1. So if you take the numbers from 1 to n and you divide them up into pairs, each pair adds up to n plus 1. And if you have n numbers, they're n over 2 pairs. So this is the sum of the nth triangular number. And we're supposed to look at the sum of the reciprocals of the triangular numbers. That's 1 over 1, plus 1 over 3, plus 1 over 6, plus 1 over 10. In general, it's 1 over n times n plus 1 over 2, and so on forever. It's the series summation, and goes from 1 to infinity, 1 over n times n plus 1 over 2, which is the same as summation n goes from 1 to infinity, 2 over n times n plus 1. Was 1 over n times n plus 1 over 2 is 2 over n times n plus 1. And I can take the 2 outside the summation if I want. That's 2 times summation 1 over n times n plus 1, and goes from 1 to infinity. And we want to find the sum of that series. Or it's enough to find the sum of this series and just multiply by 2. But if you look at 1 over n times n plus 1, and you know fractions, this is exactly 1 over n minus 1 over n plus 1. Because if you put this over a common denominator, this is what you get. So summation 1 over n, n plus 1, n goes from 1 to infinity. Is summation n goes from 1 to infinity, 1 over n minus 1 over n plus 1. And this is a telescoping sum, right? This is 1 minus a half, plus a half minus a third, plus a third minus a fourth, plus a fourth minus a fifth, and so forth. And everything cancels except the first one. So this sums to 1. Which means that the series we're interested in sums to 2. Right. Questions about this, perhaps?
Is there any other ones besides the reciprocal of triangular numbers? We didn't do anything else besides, or the squares. Those are the only 2, right?
In terms of reciprocals of integers, Yeah, we did summation 1 over n squared is pi squared over 6. And then we also observed that if you take 1/4 summation 1 over n squared, that's 1/4 times pi squared over 6, which is pi squared over 24. Of course, this is the same as summation, n goes from 1 to infinity, 1 over 4n squared, just bring the 4 inside, which is, and 4n squared is 2n squared. So pi squared over 24 is summation 1 to infinity, 1 over 2n squared, or it's the same as saying summation 1 over n squared from 1 to infinity, but only over the even numbers. And from that, you could say that pi squared over 6, which is summation 1 over n squared, is the same as summation 1 over n squared for n even, plus summation 1 over n squared for n odd, right? Because every number is even or odd, and this is pi squared over 24. So from that, we also got a formula for the sum of the reciprocals of the odd numbers, which is pi squared over 6 minus pi squared over 24, which is a 6 minus 1 over 24 times pi squared, which is 3 over 24, or pi squared over 8. So we also got from pi squared over 6 summation, the sum over the odd numbers is pi squared over 8, which is kind of interesting, but I think those are the only explicit ones that we did. Summation 1 over n cubed, no one knows what that is. That's an open problem. It has been for several hundred years. But that's all we did in that regard. The next problem was to encourage you to go back and look at the great theorem in the chapter on Isaac Newton and to calculate geometrically the area of the shaded region in the figure on page 174. So on page 174, we have a semicircle with radius 1/2, centered at the point 1/2, 0. And then we took the midpoint of this radius, 1/4, drew the vertical line, and this is the shaded region, which is labeled A, B, C, and D. So we want to find the area of the shaded region. So, and the area of the shaded region is equal to the area of the sector of the circle, which is the sector from A to C to D. So the area of the red sector minus the area of the triangle, which I'll put in green, minus the area of the green triangle. The green triangle is BCD, the red sector goes A to C to D. So I have to compute these separately. Now, if we look at the green triangle, that's a triangle where this side, this is BCD. This is a quarter. Right? From B to C, a quarter to a half is a quarter. The radius of the circle is a half. So this angle, the sine of that angle is a fourth over a half. This is the opposite side is half the hypotenuse of this right triangle, which means this is an angle which is pi over 6 radians. This angle is pi over 3, or this is 30 and this is 60. By the Pythagorean theorem, what is the height, h? It satisfies by the Pythagorean theorem, h squared plus a fourth squared is a half squared, or h squared plus a 16th is a fourth. So h is a fourth minus a 16th, which is 3 over 16. So the height, this is h squared, is the square root of 3 over 16, which is 1/4 the square root of 3. So that's the height. This is the base. The area of the green triangle, this triangle BCD, is a half the base times the height, which is square root of 3 over 32. So that's the area of the green triangle. That's the green area. What is the area of the red sector? ACD. Well, this angle is pi over 3. That's 1/6 of 2 pi. It's 1/6 of the area of the circle. That's 1/6. What's the area of a circle? Pi times the radius squared. Pi, what's the radius a half? A half squared. So that's 6 times 4, that's pi over 24. So that is the red area. So the area that we want, the area of the shaded region, is the area of the sector. This is our answer. Pi over 24 minus root 3 over 32. That's the answer.
Can you move the paper down, please? Oh, I can see the area for the sector. Oh, that's it. Oh, okay. Thank you.
Again, it's all in the book in exactly the same way, basically. But that's it. Any questions about this? Okay. Let's look at the last problem on the review sheet, which is number 12. So in the chapter on Euler's calculation of the sum of the reciprocals of the squares, he starts with, or the text starts with the Taylor series for sine of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, x to the 9th over 9 factorial, and so on forever. And the question is, where does this come from? Well, this is the Taylor series. And in general, this is supposed to be in Math 176. If you have a function f of x, you want to try and write it as a power series, a0 plus a1x plus a2x squared plus a3x cubed, a4x to the 4th, and so forth. And you have, the problem is how to compute the coefficients, say the Taylor coefficients of the series, a0, a1, a2, and so forth. Now, a0 is easy to find, because if you have such a series, if you plug in f of 0, everything is 0 except the first term. So a0 is f of 0. If you take the series and differentiate it, f prime of x, derivative of a constant is 0, derivative of a1x is a1, then you get a2 times 2x, a3 times 3x squared, a4 times 4x to the cubed, and so forth. And now if you plug in x equals 0, all of these terms disappear. F prime of 0 is a1. So a1 is the derivative of the function evaluated at 0. Suppose you differentiate a second time. So the second derivative of a constant is 0, derivative of a2 times 2, this is 2a2 plus a3, and then you get derivative of 3x squared, 3 times 2x, derivative of 4x cubed, that's 3x squared, and so forth. All the terms except the first will have some x in it. So if you evaluate this at 0, you'll just get 2a2. So a2 is going to be the second derivative at 0 divided by 2. If I take the third derivative, I'll get what? I'll get, this is 0. Here I have 6a3 plus a4, 4, 3, 2x, and so forth. All the higher terms will have an x. So if I evaluate the third derivative at 0, I just get 6a3. So a3 is the third derivative at 0 divided by 6, which is 3 factorial. And in general, the basic formula for a Taylor series is f of x is a0, a1x, a2x squared, and so forth, an x to the n. The nth coefficient, an, in the Taylor series is always the nth derivative of the function evaluated at 0 divided by n factorial. So if we wanted to use this with the sine function, suppose f of x is the sine of x. So if you start taking the derivatives, first derivative is the cosine, second derivative is minus the sine, third derivative is minus the cosine, and the fourth derivative is the sine of x again, and it keeps repeating. So if you look at these functions evaluated at 0, f of 0 is 0, sine 0. F prime of 0 is cosine 0, which is 1. Second derivative at 0 is minus sine 0 is 0. Third derivative at 0 is minus cosine 0 is minus 1. So if you look at and then it repeats, because when you differentiate the sign, it's periodic. The series of these numbers is 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. So the nth ace of n is going to be what? This is when, for the even numbers, it's 0 if n is even. It's equal to 1 if n is a number of the form 4k plus 1, so you get 1 over n factorial. And if n is 4k plus 3, you get minus 1 over n factorial. So if you look at the series for the sine of x, you only get odd powers of x. When n is 1, you get x. When n is 3, you get minus x cubed over 3 factorial. When you get to 5, it's 1 over 5 factorial times x to the 5th minus x to the 7th over 7 factorial. It's exactly the series that was written down in the text for, it's the Taylor series of the sine of x. What about for the cosine? What are the derivatives of cosine x? You have cosine x minus sine x minus cosine x plus sine x. And then the next derivative is cosine of x again. So this is cyclical. It repeats. And if you let x equal 0, the numbers you get are cosine 0 minus sine 0 minus cosine 0 sine 0 cosine 0. It's just 1 0 minus 1 0. That's just cyclical. It repeats in that way. So for the Taylor coefficients, if n is odd, it's always 0. If n is a multiple of 4, it's 1 over n factorial. So this is like 0, 4. If n's a multiple of 4n, it's even, but 4n plus 2, it's minus 1 over n factorial. So for the Taylor series for the cosine of x, you're only going to get even powers of x. And they're going to oscillate. So the next term, when you have n equal 2, this is minus 1 over 2 factorial times x squared plus x to the 4th over 4 factorial. You just get this alternating series in the even powers of x, where the coefficient of x to the n is x to the n over n factorial, plus or minus, depending on whether n is divisible by 4 or not. That's what the Taylor series for the cosine looks like.
Professor, is it 1 minus x to the,
I'm sorry, this should be an 8. Thank you.
no, the first one, I mean, is that
1
x to the what
minus
power?
x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6. All right, in general,
Do we have to write all of this stuff that you write, or we can just write that last,
if you can
4
write this
terms?
down, that's fine.
Okay.
Again, there's a sort of a hierarchy of importance in what you're supposed to be reviewing. So the most important thing is to review the homeworks and to study the great theorems in the 5 chapters. Um, that's like, those are like the two most important things, certainly. But everything else is also important, but that's really the core. And again, I remind you, the exam is Wednesday, 9 a.m. on campus in Gillette, 205, I think. But this evening and tomorrow evening, I'm on Zoom if you have questions. And so I encourage you, if you have questions, to log on. And if you don't have questions, you might log on to see what questions other people have. And that might be useful.
So for the sign, what I understand is the odd powers,
For the sign, it's
add.
just the odd powers, yes.
Odd powers, and the cosine will be the even powers.
Correct.
So there's no calculators, correct?
Correct.
And it's not open book, correct?
Correct.
Okay, I just want to make sure.
Yep. But if there is a problem that involves Cardano's formula, I'm going to put Cardano's formula on the exam. It's hard to, you don't have to just memorize that.
Thank you so much.
There are two reasons, at least, why there's no calculators. First, because for almost none of the problems would they be useful. And second, it's not fair to people who don't have calculators to let other people use calculators. So that's the way that's.
All right, so my rebuttal to that is if it's irrelevant, then it shouldn't be a problem. And what if there was a way to supply calculators for everyone?
Well, I'll tell you the story I must have told already because I repeat it constantly, which is one of my neighbor's kids who was in middle school told me she was in honors math in middle school. And I said, how is honors math different from regular math? And she said, in regular math, you're allowed to use a calculator. In honors math, you're not. So the only reason to use a calculator is to add fractions, I think. And I do believe by the time you get to this level math class, you should know how to add fractions. In any case, there's not very much calculation, so I don't see what good a calculator does, truthfully. But for simplicity, there's no calculator, only your brain and pencil and paper. I mean, pretty soon you realize they're going to implant an electrode in your brain and you'll simply have a thought and you'll ask AI what the answer is and it will just tell you and you'll write it down. But, and when that's done, I don't know how to avoid that. But since we don't yet have electrodes implanted in our brains with links to ChatGPT, we do it the traditional way. Anyway, okay, that's my story. Or as they say, that's my story and I'm sticking to it. So. Okay, see you on Wednesday.
I got one real quick question, but it's something different. So when I'm looking at the cubic, they show me all different methods. I want to know how many methods do you know to solve a quadratic?
A quadratic?
Yes.
Well, I mean, there's basically just one method, or you might say maybe there are two sometimes. Either you can factor it or you use the quadratic formula. I haven't, but they're more or less the same. Because in the quadratic formula, you're just completing the square so that you can factor it. But that's the only way I know that I can think of.
And have you heard of the PQ substitution?
No.
Oh, okay.
I mean, there are some other facts that you can use. For example, if you have a quadratic with integer coefficients, and let's say it's monic, then if there's going to be a rational solution, it's going to be an integer that divides the constant term. They're like, you know, they're like odd facts like that you can use. But I mean, the quadratic formula works in 100% of the cases, so that's fine. And if sometimes you can find a quicker way to do it, that's fine too. Okay, all, see you, if not in a Zoom session, on campus on Wednesday.
right.
Enjoy the beautiful day.